I would like to thank the chairs of this webinar for having organized the preparation of the initiative and for inviting the speakers. I would like to thank also Susan Conway, our Vice President, for having worked under the scenes to set up the organization of the International Geomorphology Week. And of course, thanks in advance for the talks that are going to be given today. The program is really exciting, so I don't want to steal any more time to the speakers. And I wish you a pleasant webinar. Thank you very much.
Okay, good morning, everyone. Thank you, the chair and the president, for giving me the chance to speak. And my name is Dongfeng Li. I'm a research fellow in the geography department of National University of Singapore. But today my presentation is about reading the story of climate change in the fluvial sediment lows in the case of high mountain Asia. Well, this work is actually contributed by many colleagues listed here. So I also want to take this opportunity to thank their contribution. Well, high mountain Asia, we know that it includes the Tibetan Plateau and also the surrounding high Asian mountains, the Himalaya, the Hindu Kush, Karakoram, and Tian Shan. So all these large Asian rivers, actually, they also originate from high mountain Asia and supporting for billions of people's of life. So for our geomorphologists, we also care for this particular region because they are also important sediment sources for the global land ocean sediment flux, if we look at this map produced by Professor John Milliman. So climate change here in the high mountains area, we know is normally much faster than the global average. This is also true for the high mountains of Asia. For example, the left figure, we can see that the temperature since the 1950s, that they increased at a rate of 0.32 degrees per decade. This is the double of the global average. And the precipitation also overall increased in the region since the 1990s. So we can see that the climate in the high mountains of Asia has becoming warmer and wetter over the past decades. And in response to the fast climate change, there are many scholars that have been done beautiful works in the region to report the retreating glaciers, the melting snow, and also the thawing permafrost. And overall, the water cycle has been changing, especially over the past decades. They also report that the total runoff in the region have been increasing in response to the increasing glacier melt and the precipitation. So as a geomorphologist, what we care for the region is to ask the following question: how modern climate change can affect the fluvial sediment lows in the region? And the first case study we did is in the headwater region of the Yangtze River. It is here, it is located in the central Tibetan Plateau. It is really a high cold environment. And in the very upstream, there are 2% glaciers. And the rest of the basin is actually underlain by continuous permafrost. And it is a pristine river, so it is a very good place to examine the climate change impacts. And we use the data from the gauging station. It has the daily observation of discharge and suspended sediment. So our fieldwork, we hope to identify the major sediment sources in this cold environment. Actually, we know that the sediment source in the cold mountainous environment could be very different from the tropical or subtropical regions, because you can see from these photos in the very upstream, glaciers are very important sediment sources, glacier and glacier erosion. And also because the majority of the landscapes is underlain by permafrost, you can see this thermal karst processes, like including the thermal erosion gully and also the permafrost source lumps. So in this work, we introduce a new concept called the mountain erodible landscape. It is defined as the most relevant landscapes, including the active glaciers, active permafrost, and active fluvial channels that can contribute runoff and sediment within a cold mountainous basin. For example, for a given day in a hydrological year, not all the drainage basin is classified as erodible landscape. Only the area below this freezing land altitude can be classified as erodible landscape. And if we look at the monthly data, we can see there's a very good correlation between the basin scale sediment flux and the area of the monthly erodible landscape. So we can see that the monthly erodible landscape in this cold environment, and it varies temporally, and it controls the basin scale sediment transport. And over the past decades, you can see that the mountain erodible landscape have been expanding due to the global warming. And here is a hydrograph that I want to show that in the cold environments, in addition to the important control of precipitation and rainstorm events, temperature and thermal urinal processes are also important. For example, here I identify several sediment peak events. If we look at the number 3 and number 4 event, these two events, you can see precipitation during these two events were very low. You can see the green bar. But they are corresponding to two temperature peaks, which means the temperature increase and the thermal urinal processes, likely through glacier melt and permafrost processes, they are controlling the runoff and the sediment in this cold basin. And then we collect more data from 28 quasi pristine river headwater rivers in the region, in the entire high mountain Asia, including the Upper Tarim River, Upper Indus River, and Upper Yangtze, Mekong, Salween, etc. So basically, we found that all the pristine headwater rivers, for all these pristine headwater rivers, the runoff and sediment flux have been increasing substantially over the past decades. And on average, for sediment flux, it increased at a rate of 13% per decade. And here, this diagram shows the time series of runoff and also sediment flux over the past decades, since from 1960 to 2017. So we can see that both runoff and also sediment flux have been increasing substantially over the past decades, and the increase actually accelerated after the middle 1990s. For example, you can see after 1995, the increase in runoff and sediment flux have accelerated. And this is in response to the warmer and wetter climate after the middle 1990s. And glacier retreat also have been accelerating in recent years, and so as to with permafrost thawing. So with permafrost thawing, the source lamps, especially such kind of channel connected source lamps, they have been increasing, and they are providing more sediment sources. And together with the increasing runoff, such mobilized sediment, they can be transported to the downstream. This is something really interesting in the region. And we also estimate the sensitivity of sediment flux to climate change. So basically, the results show that for each, we estimate the sensitivity for each headwater river. So each river has its own characteristics. They are kind of different in terms of the sensitivity. But on average, for 1 degree increase in air temperature, it can result in a 32% increase in the sediment flux. And we also found that for the sensitivity of sediment flux to temperature increase with the glacier, with the drainage basin glacier cover, which means for a drainage basin where there are more glaciers, their sediment flux sensitivity to temperature are higher. So we also, based on the sensitivity result, we did the projection for the future sediment flux by 2050. So first, we estimate the present day sediment flux in the region in all the high mountain Asia is to be 1.9 gigaton per year. And under the extreme climate change scenario, which means the temperature will increase 3 degrees, precipitation increase 30% by 2050 from the present day to 2050. And we predict under the extreme climate change scenario, by 2050, the total sediment flux in the region could reach over 5 gigaton per year. And now I will briefly discuss some of the potential impacts of the increasing sediment loads from the region to the downstream communities and the infrastructure. For example, the increasing sediment loads has important implications for the hydropower systems, for the agriculture, water quality, carbon cycle, and also for flooding. Well, in last year during the COP26 climate change conference in Glasgow, journalists from Scientific America, they interviewed us for this and reported this press release, and they used a title, "Muddy rivers are jeopardizing dams and water quality for millions of people." So basically the story is that with the increasing sediment in the region, the river surface stability has been increasing, and they are likely to degrade the water quality in the region. And if we look at this photo, this top photo, we can see this photo was shared by Kel. Kel is a journalist working in the Tibet. And the story behind this photo is that previously this is a Princeton River that the water was quite clean, and the local communities use the river for drinking. And with climate change, that you can see that this river was totally disturbed by the bank erosion and also source land events. So you can see they can no longer use this river and have to go to another place to find the drinking water source. Sorry. Okay, we also discussed the impacts of the changing sediment loads on the hydropower systems. So from this map, we can see the Himalaya rivers, they are really have huge hydropower potential, and the majority of this hydropower potential haven't been tapped. And we can see from all these red dots, they are the planned dams, and some of them are under construction. So we use the example of the Upper Yangtze River. We estimate that in the next 3 decades, from 2020 to 2050, under the extreme climate change scenario, there will be 2 gigaton sedimentation in these cascade reservoirs. And it is this 2 gigaton sedimentation. This is a large value that is equivalent to 2 times the design storage capacity of the downstream Liyuan Reservoir. The Liyuan Reservoir is now the first upstream reservoir, cascade reservoir on the mainstream of the Upper Yangtze River. With the increasing sediment loads, it can also cause the abrasion of the hydraulic bands. For example, this case in the Upper Indus River, it is a runoff river hydropower project, but this hydropower system, they face a severe sediment issue, largely because of the increasing sediment. They abrade the hydraulic bands and cause the abrasion issue. And this year, for this case example, the hydropower turbines have to be replaced within after less than 1 year of operation of the hydropower system. And lastly, I want to briefly to discuss the sediment source to sink processes in the Anthropocene and the impacts of both climate change and the human activities. So we know that for our Princeton River, Professor Schumer has introduced the concept that mountain regions are normally the sediment source, and the middle lower part, they transport the sediment to the downstream delta and the coastal regions. So however, things in the story in the Anthropocene could be very different. We know that climate change have been increasing the sediment sources in the upstream mountains, and by promoting more glacier sediment sources, permafrost soil erosion and riverbank erosion. And at the same time, in the bordering area between the upstream mountains and the middle lower part of the basin, there are many cascaded reservoirs and large-scale cascaded reservoirs that have been constructed in recent years. So the increasing sediment from the upstream mountains will be mostly trapped behind this large cascade dams, and they will not be reached to the downstream region. So we also did another study in the Yangtze River to investigate the clean water effect, the salt water, the hungry water effect they have caused the channel incisation, shrinkage of channel bars, and also the delta shrinkage, for example, in the Mekong. And I think this is really something that our geomorphology community, we need to think about how to further adapt to such rapid changes in the Anthropocene. Okay, finally, I will summarize my presentation. So basically, in the cold environment, sediment sources includes the glacier erosion, permafrost source lumps, thermal erosion gully, bank erosion, and commonly slope wash and mass wasting processes. And both over the past decades, both runoff and sediment flux have been increasing substantially and with accelerations after the middle 1990s. Temperature and precipitation are the two fundamental factors controlling the runoff and sediment dynamics in the cold environment. And in a warmer and wetter future, we predict that the sediment flux will continue to increase. And the rising fluvial sediment loads has important implications for the downstream energy, food, and environment security. And with future cascade dams, the rising sediment loads would be mostly trapped behind these dams and will likely not reach the coastal region. Okay, this is the end of my presentation, and I'm happy to take any of your questions. Thank you.
Very much. Thanks for the opportunity to talk about this bit of a labour of love over the last few years from a team of us at Geoscience Australia. The figure you can see there on the right is the Perth Canyon. And this is a feature that dominates the Perth Canyon Marine Park in Western Australia. And this talk is really to show you how we've managed to progress our two-part geomorphology mapping approach to better understand the genesis and the current activity levels of the Perth Canyon. I'd like to particularly acknowledge my co-authors, and in particular Irina Borisova, who's been the geologist in our team and who's really helped us to have a bit of a multidisciplinary or cross-disciplinary approach to looking at this feature. So geomorphology mapping of the seafloor is something that really provides foundational data sets for so many different applications. We're currently in the UN Ocean Decade, which is driving a global effort to better map our seafloors and to better realize the blue economy that is based on these data sets. And we use geomorphology maps for a range of those applications, such as understanding the distribution of habitat, for better understanding geohazards, whether that be mass movements or tsunami behavior, and also to understand risks posed to infrastructure, such as pipelines or offshore wind farms, and navigation into major ports. So it's really one of those products that needs to be standardized, not just within our EEZ, our exclusive economic zone, but also internationally, because a lot of these applications cross those jurisdictional boundaries. So looking at something like the Perth Canyon on the left here, the need for a two-part approach may not be immediately apparent. I think a lot of us can look at a canyon like this and see a number of geomorphic units, geomorphic processes that are occurring, such as those landslides on the left-hand side, which is the northern side of the canyon. But there are also a lot of features that are more nuanced. And when you start to do geomorphic interpretation, particularly in the marine realm, where you may have disparate data sets and you're not entirely sure of what it is you're interpreting, we really want to capture that uncertainty and make it quite an intentional step in interpreting geomorphology from the morphology. So part one of our two-part approach has been developed in collaboration with the British Geological Survey, the Irish Geological Survey, and the Norwegian Geological Survey. They realised years ago that they needed to standardise their approach between their jurisdictions. And so they started this project off when we joined them a few years ago to try and to also become involved in driving where this is headed. And the reasoning for needing a two-part approach is illustrated on the right here, where you have more nuanced seafloor features such as a ridge, which you can see in bathymetry. If you add subsurface information or seafloor sediment information to that bathymetry, so if you get backscatter data sets and sub-bottom and seismic, you can come up with two very different interpretations of what that feature is. And each of those alternate interpretations has really important implications for the industries that rely on those various settings. So in this case here, if you have a paleobed form, it may be that that paleobed form is providing the hard ground on which habitats can be supported. And it has implications for the sorts of infrastructure that you can put in there that if you were to build wind farms, it's not about to be knocked out by massive amounts of sediment transport. And so to develop part one of the scheme, we really just relied on the International Hydrographic Organisation's standardisation of undersea feature names. But to that, we added these illustrations of the features that they had defined. And we also added, so the comparison table on the left-hand side for a ridge shows you what that would look like in comparison to a number of other features that can look quite similar. And we minimally modified the definitions that are provided in there from the IHO definitions, because this is a well accepted and well supported scheme in the community, and we didn't want to rock the boat. We only wanted to clarify and thereby allow more consistent mapping. Part 2 of the scheme is under construction, and it's in a very similar vein. We know that the geomorphic community have some excellent and deeply entrenched classification systems for the range of settings that we might see in marine data, so fluvial, coastal, marine, biogenic, glacial settings. We've already got a lot of classification systems available to us to map these sometimes paleo systems that we see on the continental shelf. And we have no intention of changing that, only to structure it so that it looks something like this, where you have a decision tree of fluvial terms that obviously bleed down into the coastal classification systems also, with the color indicating that bleeding from one system into another and that interconnectivity. And these are basically just terms that you would use to tag the morphologies that you have mapped in part 1. And by doing so, you'd be preserving that inherent uncertainty that creeps into interpretation of subsurface forms and formative processes. So I'll spend the rest of this talk talking about our application of this to the Perth Canyon of Western Australia. We've just had this published in Marine Geology. It came out last month. I think it's in this month's volume. So you can go here if you wanted to have a closer look at this. But here's the Perth Canyon. Its morphology is that it is follows a sinuous course that is incising the continental shelf about 50 kilometres offshore from Perth and about 50 kilometres offshore from the Swan River and the Murray River. And it really contrasts with those shorter blind canyons that typify the continental slope north and south of it. And it's incised in this length here, and these reaches entirely into the Vlaming sub-basin of the Perth Basin. So we know we can do a lot with morphology, with bathymetry. We know that we can understand quite a lot of process from the energy setting that gradient provides. And so putting a long profile up the thalweg of the canyon, we can see some quite distinct zones. We've got a very steep head wall to the canyon where the cross-section of the canyon isn't very entrenched. Becomes more entrenched through this lower gradient reach, which is more mature, where you get a whole series of nick points also occurring. And then you get a much lower gradient reach here. This reach is actually between the C cross-section and about the E cross-section. And this is where the canyon has been deflected northwards. It's deflected by 90 degrees northwards and has obviously hit, we would assume, a hard substrate to redirect it along that course before the canyon then manages to emerge out from the continental slope and discharge onto the abyssal plain. So we can do this with bathymetry data that we've got from the Oz Seabed platform that Australia is heavily involved in. You can go there and get a range of different bathymetry grids for areas of interest yourselves. Then we applied some semi-automated mapping approaches to that bathymetry data set to essentially pick out the key features that we thought would be of interest to provide us with insights into the development of the canyon. And the sorts of features you can see dominating were the ones that were fairly obvious from the first figure I showed you, these what we call gullies on the northern wall, but also these broad terraces in the headwaters and these steep escarpments that define some of the more subtle topographies or bathymetries external to the canyon. So step 2 is to assign geomorphic interpretations to each of those shapes. And to do that, we use a lot of different data sets. And this is a really nice demonstration of the sorts of data that we have at GA that you can pull together in an area of interest like this and get really extend your knowledge of what's probably going on there. This illustration here is the backscatter data set that you can get from the Oz Seabed platform. That tells you something about the hardness of the seafloor, potentially the thickness of the accumulation or the grain size of the sediment on the seafloor, but it's best looked at in conjunction with grab samples, which are shown by these dots. And what you can see is that the grab samples taken up on the shelf here, this is grain size versus depth. The coarser grain material tends to occur up on the continental shelf. You get some still reasonably coarse fine sand, further down on the slope. But within the canyon itself, it's dominated by this draped, muddy, fine-grained material, with a single exception where you have this sample here. This is all of the material that we have within the database in a 20-kilometre buffer around the Perth Canyon Marine Park. So this is all we have, but the only deep sample we have is actually quite coarse and matches what you see up on the continental shelf, and is a nice illustration of the likely transport of material through the canyon and its deposition via turbidity currents on the lower canyon floor. And that single sample is actually taken from the top. It's the lag material at the top of this core here that represents the 10-centimetre fining upward bed sets of turbidite deposits, and possibly a switch to more inactivity or winnowing of material rather than continued thick accumulation of these bed sets. Going a bit deeper, we've also been looking into the NOPAMS database at GA using some of this quite vintage data that was used for early exploration for basin exploration in the area from the 70s and 80s, but we've repurposed it to look at the shallower geomorphology. And here you can see this Valanginian unconformity surface from the early Cretaceous, which controls a lot of the morphology of the canyon. You can see this large block has glided down downhill from this headwall fault and is situated on the floor of a tributary canyon. In this example here, you can see that a lot of these deeper faults stop at the Valanginian unconformity surface, but some of them extend through, and where they do, they tend to form the headwalls of slump failures. And then this final example here, from which the flank of one of these features was cored in that slide I showed you earlier, you can see these internal surfaces are dipping upwards, upstream into the flow, into the direction of the flow. And this is at the exit of the canyon. And we interpret these to be cyclic steps, so aggradational cyclic steps formed by super energetic, supercritical flows driven by the turbidity currents. So putting that together and tagging all of those morphology units, we then come up with this geomorphology map, which essentially describes these slump scars on the northern wall. The slump scars dominate the northern and upper parts of the canyon. They also destabilize the toe of this 20-kilometre by 20-kilometre slab. Over here, we've got seismic from around the perimeter of this slab. We can see that those faults are giving way right through the Valanginian unconformity, and that this toe is the cause for that destabilization at this end. And we see a similar pattern at the upstream end of the canyon here, where the destabilized toe of these large slumps is causing these massive slab failures above them. You can also see these cyclic steps that we've mapped out at the exit of the canyon onto the fan. And we use that good data there to infer locally to this area here, where the canyon has come through a constriction, it's been deflected northwards, and the flow expands, and where it's accumulated similar cyclic steps. Some of these cyclic steps are 300 metres or so high. They're enormous features. But interestingly, also, what we've been doing is looking at the seismic in detail within the depot centre of the Hlaing sub-basin that has quite a lot of seismic available to it. And in that, we looked for any evidence of former Paleo Valley incisions that may have initiated the canyon. And the data stops about here. And what you can see is we have this Paleo Valley belt that's quite broad and quite long above the canyon headwall. And that Paleo Valley belt is situated approximately here between the Swan River, and it comes down through the Bathurst syncline. This is the paleotopography over that Valanginian unconformity surface, and we can just see that the canyon has very much followed the Bathurst syncline. It's been blocked by the Edwards Island block that was a paleotopographic high, and this Harvey transfer zone that's heavily faulted. We can see that the canyon has capitalized on that faulting to flow through there. And to look at these canyons, these paleo incised valleys, the first one of these we can see, Paleo Valley 1, formed in the late Cretaceous, when we know we had pronounced glaciostatic sea level fluctuations, and we had a very wet climate, and we had the flows coming out of the Paleo Swan River and driving those hyperpycnal currents to initiate the turbidity currents down through an offshore canyon. We see another major incision here in the mid-Oligocene, which was another period with pronounced glaciostatic sea level fluctuations. And interestingly, this is also the time that the fluvial network over the Yilgarn Craton of Western Australia tilted towards the west. So that was when we captured the flow that formerly flowed southeast for it to flow west into the Paleo Swan River. And while the climate was drier than it had been in the late Cretaceous, it was still quite wet, and it had that enlargement of the canyon of the catchment area.
And the very last incision, Rachel.
Yeah,
can you finish up in a couple of minutes?
Yep, no problem. Thanks. The last of the Paleo valleys is Paleo Valley 3. We have less time constraints on this one, but we can see that it would most likely correlate with another major paleostatic sea level fluctuation at about 5 million years. And what you can see is this progressive decrease in Paleo Valley scale from the late Cretaceous through to the present, which corresponds with the results we had when we compared the seafloor before and after some seismic events, some earthquakes in 2018. The pattern that you can see here up on the canyon head wall, which we had expected might be more pronounced, is actually quite subtle. The red is evidence of seafloor lowering. We subtracted the pre-earthquake grid from the post-earthquake grid. So this is evidence of gullying in this area, and transport down this channel and deposition very proximal to its source. So it didn't move a lot. And it really does support that idea that the Perth Canyon Marine Park is dominated by a fairly relic canyon that still has some events, but is not posing a massive threat to generally large mass movements. So I think I'm probably over time, and I'll just leave it on this slide for a moment just to say, yeah, we're presenting a draft of this scheme at the GeoHab conference, which you can attend online in May in 2022. And a couple of months later, we'll be presenting a full draft of this to a workshop at the IAG and Aaron McAuliffe's International Conference on Seafloor Landforms, Process and Evolution. So if you'd like to get involved, please email me or attend these conferences, and you'll hear more. Thanks.
Good morning, everyone. My name is Thwe Hlaing, ex-director from Yangon University of Education. This study is when I was in Tokyo. At the time, I got the GSPS fellow. At the time, my study is here, but I left from Tokyo last 6-7 years ago. So today I only want to share about only a few research for my study. Here is the data is the environmental changes of the Ayeyarwady River. Here is the Ayeyarwady River. Ayeyarwady River is one of the biggest river in Myanmar, and it is across the whole river. Here is my study area. First of all, I would like to introduce my Ayeyarwady River. The Ayeyarwady River is, as you know, one of the largest river in Myanmar, and it's drained an area of 85,000 kilometers square, and it is the 30th the world in terms of water discharge, and 55th largest spadine loads, and 4th highest total dissolved load of the world rivers. The sediment loads are the highest in the world among its river of the capable catchment sites. Therefore, it is very important, and for the largest remaining natural rivers in the world, the Gordon in 1885, he checked the Ayeyarwady River about the magnitude and the duration of flood events, and he calculated the required size of the size and height of lake embankment in the delta area. But the Robertson in 2007, he also recalculated about 10 years average total annual discharge and suspended loads from using the Gordon report. But the Ayeyarwady River, the information that Ayeyarwady rivers are very rare, as you know. That is why at the time I like to study this area. So I checked some discharge and sediment discharge and geomorphological mapping. Here is the delta area. That red parts are the embankment dike area of the apex of the Ayeyarwady delta. We can see, but most of the dikes are broken. And this day, the dike is the only landfill dikes and that area. That is why every rainy season the flooded areas are here and there, and most of the areas are submerged in that area. The purpose of my story is to provide the landform combination of the landform combination of that data plane in lower Ayeyarwady River, making geomorphological land classification maps. The second part is to provide the relationship between the fluvial geomorphology and discharge, sediment discharge and sediment phases of the environmental restoration. The third one is to examine the floodplain sediments and sediment records near delta area and to restore environmental changes in Holocene and to obtain the long records of the fluvial environmental changes of the Ayeyarwady delta area, Ayeyarwady delta. Here is my study area. Here is the TM condition, and some here is the main river course. This figure shows that the annual rainfall condition. Here we can see this part is the lower delta area. The annual rainfall conditions is about 3,000, 4,000, and here is the river bank in the summer season. Here is the river bank in the summer season and the delta area. Here, and we can see river bank condition in the summer season. Most of people are come to grow some beans and rice and so vegetable and so on. We can see in the summer season. Here is the annual discharge condition. We can see the red color line is that the annual discharge is decreasing, and the blue color line is the rainfall is increasing from 1985 to the recent. In the delta area, here is the runoff condition. Runoff condition is also slightly decreasing, but the discharge is the fluctuation we can see here, and then here is the mean discharge at the delta area. We can see, and here is the rainy season. We can see the discharge fluctuation is here. Then here is the water level condition. We can see from water although the discharge is decreasing, but the water level is increasing, and during the rainy season. And this data is I got from the India meteorological department. Here is in my country we can get only from 1944 to recent data. You can see that is why I combine with the old data and the in my country data. Here's my study part. I checked the geomorphological mapping using topography maps, satellite image, Nanson data, and digital elevation model. The second part is I check the sediment records by using Bogo data. I drain only about the 30 meters in the delta area. Then we can check the we can check the sediment condition. Here is my study part. So the first part is I check the geomorphological land classification map, especially micro geomorphological land classification map. Then we can check the fluvial landform characteristics and flat zone and surface features. Then the second part, so we drill the pool about the 13 meters, and then grain site distribution. We check the grain site distribution analysis. Then check the ECPH and measurement, and some parts. So we could check the radio carbon dated analysis for the age of the sediments. Then we can compare the grain site distribution of the sediment and structure of the sediment pool, and then how is the changes of the river channel course and flat zone with geomorphological land classification map. This is my here is the flowchart for data process for geomorphological mapping. We can we overlay all of the layer, the DM layer, topography map, and satellite image, and using area photo or orthophoto condition. Then we trace we trace some geomorphological features, and then we transform the geomorphological land classification maps like here. Then some parts we check from 1944 to the recent the river courses, along the river courses, how it changes, and which part is the increasing and decreasing, and so on. Then we here is the we make the geomorphological land classification map detail, especially natural lavine, former river course, back march 1 and 2, and water body and river. Here we can see very clearly. Here is the former river course. Here the red colors are former river course. We check the detail. Then some parts are meandering scales inside of the river. Here is the point bar development here, and here is the valley play and lower terrace and upper terrace. And here is the back march 1 and 2, which could check detail. Here is the only a few parts we could check all of the delta area. And the natural lavine parts, small on natural ravines are natural lavine parts, small red yellow color is here. The small natural lavines, are developed in the steady area, and several old natural ravine has been detected, deserted. The former river course here. The three these areas are showing narrow, hollow, and sometimes the water surface remains in the dry season, and the rainy season, so the flat water is throughout the former river course. Here is the back march 1, an area is the seasonally flooded by surrounded river. It is the submerged and the submerged water in the every rainy seasons and every year. The back march 2 here, this color is back march 2, and this area is seasonally flooded by surrounded river. It is usually covered by inundated water and wet throughout the years. Here is the water body.
About 4 or 5 minutes to go, please.
What?
4 or 5 minutes to go, please.
Okay.
Thank you.
Here is the whole delta area. I could check the microgeomorphological mapping. Then I could check the topographic relief section using the cross section. We can see that some parts are the 1 to 15 meter height, and here is the like the swamp area is here. Here is the former river course and so on. I could check all of the delta area. Then we can see here the highest is about the highest area is about the 60 meter, and on the mountain and hilly west is between pass through the area of natural levees. And here we can see I could check all of the where is the Triton mountain, where is back march, where is natural levee and former river course, and some parts here is the pleistocene in terrace and so on. Then we could analyze the grain site distribution here. We can see that is the lower parts of about the 28 meter to 29 meter depths. Most of the sediments are, we can see, marine, sandy, and gray marine, and clay with some lamination layers. And here is the about the 8 to 10 meter depth median high grade sand with the high energy deposition. We can see. So I could check the column, sediment column. We can see some parts are, I could check the radiocarbon age. It's like about some parts here, this part is the lower part is about 7,200 years ago. You can see so PP years, that is why last 9,000 years ago we can see and the 28 to 29 meter depth. We can see here is the mud content is over 50% and easing range is about 198 to 300 meters. So we can see very clearly these sediments are marine sediments. So we can see deposition and environment of this unit is we can interpret as the marine sediments. The second part is the low middle part is about 23 to 558 meter depth. We can see here also we could check. But these areas is composed of very coarse dark gray and medium sands. Easing range is 81 to 231. The mud content is about only 8%. Then we could, this unit B radiocarbon dates is ranging from 1 to 7.7 per year. So this unit interprets as a tidal influence channel fill to host much sediments. This part is the upper portion is the light brown coarse sands with only 1% mud contents, and easy range is very less than 100. Only 100. Underground water quality is different, and contamination with dark color organic matter. There are meandering river channel with different duration. We can see if we compare with the geomorphological map and sediment cold or sediment cold condition. The lowest parts or lowest portion of the unit C is consists of the reddish brown, watered clay. Also, we can see the unit is which is the surface. Soil, floodplain, and natural levees sediments. So we can see, therefore, this unit is interprets as fluvial sediments. Unit C.
Okay, we'll have to finish in 1 or 2 minutes, please.
Okay.
Thank you.
So,
right.
We can see here is the DJ organic material stating age, and then we could check the carbon age curve for the drilling borehole and estimated annual deposition rate gauge. Then I like to conclude my presentation the geomorphological land classification is very useful and grateful for flooding and natural disaster or hazard problem in my study area. This result is only the first of the introduction result for my country and for the Delta area. The radio cover deck result of the draining borehole can classify sediment characteristics of delta areas and detail. And we can see cover deck also. We can know how Holocene the rapidly before Holocene periods, because we could classify the date and cover materials. And the result of the geomorphological feature and sediments are different from other Asian rivers such as Yangtze River, Yellow and Mekong rivers, because Ayeyarwady River have not been strongly influenced by anthropogenic activities. So we could give really ordinary result of the environmental changes of the delta. So this study should be considered as a very good next step for hazard and risk assessment based on Holocene fluvial process. Okay, thank you so much for the presentation.
Okay, on behalf of our team, especially Mr. Garas and Mr. Agot, I'll be presenting this tourism impacts to karst environment in the Philippines, a case of study of two contrasting geomorphic terrains. Please be guided by this outline of my presentation. The Philippines lies in one of the most active tectonic margin in the world. It is situated in the Western Pacific region, bounded by multiple crustal plates. The Philippines is commonly defined as a mixture of an island arc-derived Philippine mobile belt and continental-derived Palawan microplate continental block, traversed by active fault systems and deep subduction trenches. Several ocean climate systems are affecting the annual rainfall pattern of the Philippines. Approximately 20 typhoons pass through the Philippine area of responsibility every year. El Nino and La Nina pattern modulates the interannual rainfall variability, while monsoon dictates the seasonal rainfall shift. The formation and development of the Philippine karst could be attributed to three major factors: the presence of carbonate rocks, tectonic climate, and tectonic setting. Unique karst features are product of both solutional and polygenetic degradation of carbonate rocks, which are strongly influenced by tectonics. So here are some karst features that shows indicating tectonic influence: structurally controlled cave development, the jointed sinkholes, cave development controlled by periodic uplift and subsidence, presence of CNACH, tubular cave system. Next. Because of the geologic, tectonic, and climatic conditions of the country, formation of tropical karst is common. Karst landscape are evident in Permian, Jurassic, Cretaceous, and Cenozoic limestone and carbonate-rich sedimentary sequences. The MGB started in-depth study of our karst only in 2013, after a high-magnitude earthquake of 7.2 magnitude devastated an island province that is characteristically karst. The earthquake uncovered amazing but dangerous karst features beneath the surface. Here are some of the examples of the beautiful karst landscape in the Philippines. The Kigel karst of Bohol, known as the Chocolate Hills, because it resembles giant chocolate kisses. It is composed of 1,776 isolated limestone hills. We have also here submerged Kegel karst, Pinnacle karst, Tower karst, Karst Ridge, and Karst Plain. Here are these amazing features are some of the top tourist sites in the country, bringing millions of revenues and employment to the Filipino society. However, without the careful management in the absence of science-based laws and policies, these karst landscapes are vulnerable to natural and anthropogenic changes. They said it is not karst, if there are no caves. So as of 2020, we have assessed a total of 864 caves, and we are still counting. Karst is one of the most fragile environments, and combination of factors could result to degradation of karst landscapes. Urbanization and tourism pressure are some of the human-induced factors of karst degradation. These scenarios are well documented in the Boracay Island, El Nido, Palawan, and Panglao Island, Bohol. These are the tourist destinations, top tourist destinations of the country. Due to poor management, pollution, deforestation, and land conversion, nearly destroyed the beautiful tropical karst landscape. Actually, in 2018, the government has started the rehabilitation of Boracay Island. Karst is beautiful, but also dangerous. If we don't know the natural condition, both natural and anthropogenic factors could potentially exacerbate the inherent geohazards connected to karst, some of which are landslides, sinkhole collapse, and flooding. Due to these movements, we are implementing the climate-responsive karst management for sustainable tourism, the Field Karst program. This presentation will highlight the preliminary findings of the Field Karst program, Year 1. The project aims to understand the effects of natural, climatic, and anthropogenic factors in the development and degradation of karst systems, especially in key tourist destinations of the country. The two study sites are El Nido, Palawan, and Siargao Island. El Nido is part of the Palawan microcontinental block at a technically stable terrain relative to the Philippine Mobile Belt, where Siargao Island is situated. We reviewed existing geological and land use data. We analyzed remotely sensed data for initial geomorphological study. During field surveys, we conducted geological and geomorphological mapping. We collected water samples, conducted in situ water quality check, and laboratory-based hydrochemical analysis. The data will be used as input to geohazard models and ultimately to set the carrying capacity of these tourist sites. Geological mapping of Siargao revealed the occurrence of microgabbro and basalt as part of the basement dinagat ophiolite complex. The deposition of thick early to middle Miocene limestone, late Miocene to early Pliocene mudstones, Pliocene to facies clastic rocks, and Pleistocene limestones are all part of the post-ophiolite emplacement sedimentary cycles. The age of the Miocene limestone and mudstone are determined using presence of large benthic and planktonic foraminifera. The facies clastic layers have no datable microfossils. The Pliocene age is tentatively designated because it is stratigraphically situated between the late Miocene to early Pliocene mudstone and Pleistocene limestone. Majority of limestone exposed in El Nido belong to the middle to late Permian mini-log formation based on the occurrence of Permian fusilionids. These are exposed in Baquit Bay and Jewel Valley. Coron formation, although limited, is exposed in Emorigi Island and Abirawan. We classified tropical karst stages of evolution using the limestone extent, elevation, slope, and surface geomorphic features. Young and mature karst were observed in Siargao Island. Young karst represents the early stage of karst evolution with low elevation, undulating terrain with embryonic dissolution features. These are observed in the young uplifted reef terrace platforms of the general land. Mature karst is characterized by karst platforms and plateaus, ridges, windows, and cockpit topography, large sinkholes, uvalas, and foliae. In Siargao, mature karst have high relief from 65 to 180 meters elevation and low relief 22 to 64 meters elevation, Kegel karst topography. In El Nido, represents the old stage of karst evolution. It is characterized by distinct remnant features and landforms such as totally isolated cone hills, high tower, and pinnacle karst. Karst towers and pinnacle karst are the dominant feature in El Nido. pH, electric conductivity, and total dissolved solids were measured in water samples collected from wells and springs in El Nido and Siargao. Conductivity and total dissolved solids are usually proportional to salinity at 1,300 micro per centimeter or 0.6 PSU and above in red line indicates a possible saline water contamination in the groundwater. Groundwater samples of El Nido are below the threshold limit and could signify less influence from saline water. However, samples from the coastal urban areas have relatively high salinity. Siargao has relatively higher salinity and electrical conductivity values compared to El Nido. This trend will be examined further if this is a natural or anthropogenic phenomenon. It can be noted that natural mixing of sea and fresh water via cavities and voids are highly possible in limestone, especially in tropical island karst. Compared to El Nido, a large percentage of the total population of General Luna and Del Carmen in Siargao is living in karst. Since most of the communities are living in the estuaries and coastal zones, saline water mixing intrusion is possible even without the impact of overpumping. Any development for residential, industrial, and tourism purposes will have an impact to the karst landscapes and karst groundwater resources. This aspect will be further considered in the formulation of the karst management plan in year 2 of our research project. This project will also investigate the geohazards in karst. Landslide susceptibility maps were updated using the data collected from the 2 sites. The maroon and red zones are the critical and highly susceptible to landslide occurrence. It was noted that rockfall is the dominant mass wasting type in limestone, evident in Permian, Jurassic, and Miocene limestones of the 2 study sites. The breeze slide is the dominant mass wasting typically in highly weathered conglomerate and quartz diorite in El Nido. These maps are just preliminary since hazard modeling will start in the year 2 of the project. For the summary, Siargao is underlain by Miocene and Pleistocene limestones, while El Nido is underlain by Permian and Jurassic limestone based on field mapping, petrography, and fossil age dating. The Permian and Jurassic limestone of El Nido show the most advanced stage of tropical karst evolution. Miocene and Pleistocene limestone of Siargao show mature stage of tropical karst. Due to the inherent porosity and secondary active cavities in the limestone, natural mixing of saline and freshwater is highly possible in tropical island karst. With excessive groundwater extraction, karst aquifers in island karst are vulnerable to saline water intrusion. Ways forward, pressure from the rapid urbanization and tourism exploitation of the beautiful island karst of the country could lead to anthropogenic contamination, such as heavy metals, fecal coliform, etc. of karst aquifers and frequent hazard occurrence. For the year 2 of our project, the following will be implemented. Heavy metals and fecal coliform levels will be measured in the water samples from the 2 sites, particularly urban and tourism centers. Geological and geomorphological data will be used as input to the karst-specific landslide and sinkhole hazard modeling, and carrying capacities of these tourism areas will be calculated, considering the geological information as one of the factors. The karst-specific hazard models will be the basis for ecosystem-based disaster risk reduction and management. Thank you for listening. Mabuhay.
Thank you. Well, good afternoon, everyone. Selamat siang, Swati Ka. Obviously talking to a lot of people from a lot of different places. It really is such a pleasure to be able to talk in this conference today. I've been striving for a long time to bring the sort of disciplines of biology and geomorphology together in a more tangible way. So this is a really great opportunity to showcase that. So I have a lot to talk about, so I'm going to just get going now. So for a long time, people have been interested in why species are found in some places and not others. So I've drawn on the map here Wallace's line, because he recognized very early on that Sumatra and Java had animals much more like the Asian mainland, whereas New Guinea was much more like Australia. And we know the reason behind this broad difference is because even in times of low sea level, the region remained a water barrier for more than 50 million years. So many people would consider Darwin and particularly Wallace as the fathers of modern day biogeography. They made maps to visualize species distributions and how they change over geographic space. Geology and Earth history are fundamental to the study of biogeography, and these two men, coincidentally also called Charles and Fred, played very important roles in putting species distributions in context with Earth history. So Lyle made the connection between fossils and contemporary patterns, while Wagner, of course, proposed the theory of plate tectonics. So of course, these days, biogeographers have much more to go on than just fossils, plate tectonics, and species distribution maps. Molecular genetics has really revolutionized the way that we study the relationships between organisms, their origins, and their evolutionary history. And modern DNA analysis is revealing all sorts of surprises about the evolution of biodiversity. So here are a couple of famous examples where genetics has completely changed the long-standing biogeographic hypothesis. So here, passerine birds, the songbirds, were for a long time thought to have been recent immigrants to Australia. But actually, it turns out we now know that they originated in Australia before spreading all across the globe. And similarly, the pythons is the complete opposite side of the story. We thought that pythons originated in Australia. It turns out that they actually came out of Africa, and they arrived in Australia much more recently in the Miocene. So not only can we reconstruct relationships to see which groups are more closely related to who, we can also use genetic data to gain an understanding of the timing of divergence, so when species arose, be that by using fossils or geological calibrations or by the rates of genetic mutations. And we can also get an understanding of past population demography, which I'm going to talk about a little bit later. So I'm a postdoc in the Division of Ecology and Evolution at the ANU, and I've spent much of the last 17 years studying the biogeography of Australian reptiles. Unlike most of the biologists I work with, I have a background in earth sciences, so I did my undergrad in geology, and I really use this perspective a lot to try and make sense of the genetic patterns that I uncover. So in my talk today, I want to show you how I use molecular studies, mostly of lizards, to explore some emerging patterns and put this in context with the evolution of Australia's landscapes. So the reptiles and amphibians that we have in Australia represent a mixture of groups that have been here for a very long time, and so things that originated in Gondwana, and also things that have arrived in Australia after the breakup of Gondwana. So a large number of our endemic geckos, including so these things, legless geckos and myobatrachid frogs, are examples of things that became isolated in Australia following the breakup from Antarctica more than 50 million years ago, whereas our goannas, snakes, and dragon lizards arrived much later when the Australian continent came in close proximity to the Asian mainland. So regardless of whether our biodiversity was Gondwanan or not, whether it arrived later, the animals that we've had here have been here for quite a long time, probably at least 25 million years. And a lot has happened in Australia regarding kind of cosmetic changes to the continent in that time. For example, I guess while our mountain ranges, or what we call mountain ranges, which is not what some of you call mountain ranges, it's all relative. But these sort of areas that I've highlighted in brown here may have been tectonically stable for a long time, 100 million years or so. There's a lot that's sort of happened much more recently in the last 50 million years or so. So we've had uplift of the Great Dividing Range along the East Coast. We've had uplift of the Flinders Ranges and areas down here a lot more recently, maybe in the last 5 million years. But what I find the most fascinating about our landscape history is the fact that this huge area, now occupied by the deserts and dune fields in the centre of the continent, has really only sort of existed in maybe the last less than 1 million years or so. And this extremely drastic change over such an enormous part of the continent would undoubtedly have had a huge impact on the evolutionary history of the animals and plants that were living in this area. So of course, at the same time that the landscapes have been changing, the climate's been changing, these things go hand in hand. And in particular, from around 15 million years ago, things started getting colder and drier. And in these cold periods became deeper and longer during the glacial cycles of the Pleistocene. So I've been trying to make the geological literature and the history of the Australian landscapes more accessible to biologists. And I've published a number of synthesis papers that basically try and outline the relevant geological literature for a region, and then I collect genetic information from different groups to try and see if there are broad patterns emerging. And the most recent of these papers came out last year, in which I attempted to take an area as large as the Australian arid zone and to think about the ways in which the evolution of the landscapes there may have shaped the genetic patterns of animals. And in fact, the Australian deserts contain the highest diversity of lizards anywhere on the planet. So they really are a great system to explore by geography. So the arid zone is one of those places that hasn't readily left a lot of clues as to what existed before. Much of the centre and the west of the arid zone is non-depositional, and fossils don't preserve very well in arid environments. So it seems like basically we need all the evidence we can get from different disciplines to piece together the history of the landscape. Now, there is absolutely no doubt that biogeographers need earth scientists to help us understand why and when animals may have been displaced. But what I want to do in this talk is to try and convince you that earth scientists might actually also be able to learn about the geological or geomorphological history of the arid zone through the deep history recorded in the genes of modern animals. So because a lot of you probably have very little idea about evolutionary genetics, which is totally fine, I wanted to briefly touch on the way that I approach the work I do. And I'll demonstrate this using a case study from quite a few years ago now, but one that I think is very intriguing and clearly demonstrates the importance of geomorphology in shaping the genetic patterns of a living species. So this is a little terrestrial gecko. It was once considered a single species that had a distribution across the entire arid zone. What I did was I took genetic samples from museum collections. So I took a sample from every one of these points and sequenced the DNA to try and figure out whether there were multiple distinct species or whether they were in fact one big population, whether it was all the single species. And what I found was that we did indeed have multiple genetically distinct groups. So you can see this is a phylogenetic tree here on the left. And you can also see that these different genetic groups have discrete geographical distributions. And while I was thinking about the distributions of these groups, or clades as we call them, I came across a map of the major drainage divisions across Australia. And I was particularly struck by this little skinny Bolu-Bankania basin in purple here. So, you know, I mean, you can see for yourself, it does seem like the distribution of these groups is remarkably delineated by the drainage divisions. Now, this isn't actually weird for an aquatic organism like a fish. We know their distributions are often constrained by drainage divides, but this is a terrestrial gecko. It lives down spider burrows, and the reality is that there's nothing really stopping them from traversing these divides. It's not like there's a big mountain range that separates the drainage divisions. In fact, in many places, you could walk from one drainage divide to the other and not even really notice that you've done that. So the conclusion that I'm currently running with is that drainage divides are separated by ridge lines, and even if they're small, ridge lines represent the driest parts of the landscape. And during glacial cycles, these areas would have been even drier, perhaps even devoid of vegetation. And this, populations could have been displaced towards the centre of the drainage basins, potentially for long periods of time, and became genetically isolated there. So that was from a little while ago, but basically we've got data sets now accumulating for lots of different animals and plants, and the sampling for some of them is getting really good. So we're starting to get genetic representatives from across the arid zone. And the last couple of years I've been working on collecting genomic data, so thousands of molecular markers for 10 different species across the whole arid zone, sampled very finely. Unfortunately, I don't actually have that data in hand. It's a work in progress, but I want to tell you about the sort of things that I've been thinking about in terms of how landscapes and geomorphology might be important for the generation of biodiversity. So we know from studies across the world that geological diversity is positively correlated to species richness. In Australia, we know that there's incredible species diversity and what we call microendemism, so things that have very, very small geographic ranges. We know that there are just tons of these things across the top end, the Pilbara, Queensland coast. But the arid zone is not a homogeneous blob either. It's not, there's lots of areas where it's quite diverse. We've got 10 different deserts. They're different ages. They have different substrates, the topographic uplands, riverine lowlands. So yeah, our dune fields are also remarkably vegetated, and there are very few regions that currently have active dunes. I think that there's this general misconception, especially among biologists, that the arid zone in Australia looks a bit like this, like a desert in the Sahara. I once mentioned this in a lab talk, and someone who had spent a lot of time in Northern Africa said that there's actually a general misconception that people think that the Sahara looks like this too. But actually, I think a lot of the Sahara is actually a lot more geologically diverse than this too. So I have put up here 3 questions that I just have been thinking about that I feel like it showcases the unusual way that genetics could actually be useful to a geomorphologist. So the first question, do terrestrial species show biogeographic breaks consistent with water or lack of water in the deserts? And I think in the arid zone in particular, water is a limiting factor for all life. And so the accessibility of water would undoubtedly have been a driving force behind the evolution of biodiversity, like I showed you with the little geckos before. But water or rivers can also act as biogeographic barriers. It can lead to genetic isolation, or they can also facilitate dispersal if you're an aquatic organism. So here are lots of nice examples where the history of ancient rivers are recorded in the genetic signatures of modern animals. And this is a great study that came out recently, demonstrates this biological and geological synergy and how tectonic activity mediated the isolation of freshwater habitats and influenced riverine biodiversity. So the authors used the genetic signatures of different types of aquatic animals to show how a major Pliocene drainage rearrangement event in the Lower Murray-Darling led to the evolution of distinctive and isolated groups of species in the Glenelg and Wimmera drainages. Australia is also very famous because there are lots of cool studies that have come out recently that show how this extraordinary diversity of subterranean fauna has evolved in the Yilgarn and Pilbara areas alongside the evolution of the calcretes there. So the Yilgarn region contains over 200 large isolated calcretes, and basically every single calcrete aquifer has an entirely different suite of organisms that are basically only found in that calcrete. And so the genetic data can tell us about which calcretes are connected during rainfall events or which ones aren't, which may have something to do with the nature of the intervening regolith. So that's, yeah, another example of how these two disciplines can inform one another. So second question, do terrestrial species show biogeographic breaks consistent with geomorphology or geological boundaries? This example comes from a study I did in my honours, which was ages ago, but I still use it as a nice example to demonstrate this. I was looking at the genetic patterns across the Pilbara region in Western Australia. And once again, we had what we thought was a single species, but we wanted to know if maybe it was more than one, because some looked a bit different than others. What I love about the Pilbara is that you can really see even from space how differentiated it is compared to the surrounding landscape. So this is the Pilbara Craton here. And this just shows different sort of broad geological units. And once again, we found that there was actually a lot of genetic diversity within this thing we were calling one species. And you can also see again here that the distributions of each of these groups, they're discrete. And so, you know, these different geological units are quite distinctive with distinctive habitats. So these granites in the north are very different deep soils compared to these ironstones in the south, shallow soils, and they again are very different to these young sort of sand plains and things that exist around the edge. So this was a study from a long time ago, and much more recently, lots of other people have been looking at different things in the Pilbara and finding the same patterns. So this is an example of some spinifex grasses, but similar patterns have been found in spiders and beetles and things. So it's potentially a much more widespread pattern than we originally thought. And this is an example, so that was an example of more local scale geology. This next example is potentially much broader and is only something I've just begun thinking about. But I recently came across a map of major crustal boundaries of Australia. Now, each one of these crustal blocks has a unique geochemical signature. And so the boundaries between them mark the area of geochemical turnover, and they also often have a fault or some other structure at the surface.
Dr. Pepper, you have 5 minutes remaining.
No worries, thank you. I've been thinking a lot about this map because almost all of the common biogeographic boundaries that we see in plants and animals in Australia occur at the same location as these deep crustal boundaries. So this is just a summary of tons of different genetic studies, and you can see, I guess, for example, you know, that they sort of match where these deep crustal boundaries are. And it turns out that Elizabeth Buey from CSIRO has looked at the diversification of eucalypt species in Australia and found that diversity coincides with variation in geochemistry, which makes sense for a plant and is very cool. But we can actually see this sort of correlation at a much finer genetic scale. We have data sets, so this is a data set of a skink that came out of our lab quite a few years ago now, but you can see that even at this genetic level, these different groups within a single species are differentiated by at the same locations as these deep crustal boundaries. So obviously this phenomenon requires testing in like a comparative and a statistical way, but what I thought would be very neat is that the boundaries are actually not, so you can see here the confidence levels, they're not mapped with the same degree of confidence, and there are large areas, particularly in the arid zone, where they're not mapped with any confidence at all, largely because they're often buried in 30 metres of sand or something. But animals and plants living in the region before the development of the dune fields might have recorded in their genetic signatures these biogeographical breaks. And so they might actually be able to be used as a proxy for the location of these deep crustal boundaries in these areas where currently the geological information is very limited. And finally, I just want to wrap up this talk with another thing we can do with genetic data, and that's to reconstruct changes in population size for a given species or a population through time. So we can see whether populations have increased, decreased, or remained relatively stable through time. And so we can view these changes using skyline plots like this, and the different colours represent the contribution of different regions to the overall population size through time. And you can see that in the case of the species on the left, its populations remained relatively stable, with a very recent population expansion here that began around 1 million years ago when the deserts were beginning to form. Whereas for the species on the right, you can see that the population went through a big decrease or a population bottleneck here just prior to re-expanding again around 500,000 years ago. So I think as these desert biomes were opening up, these arid adapted things were spreading into these new areas. So what I'm interested in, and it's great, I can see Paul in the audience, so this is something I've been thinking a lot and talking to him about as well. What I'm interested is to what degree population expansion is synchronous, both within and across different deserts and also across different animals and plants. Because if we could reconstruct population demographic histories for a bunch of different organisms and also put dates on the timing of those expansions, if we found that lots of species were clustered around the same dates, it might actually tell us something about the evolution of the dune fields, which, as you can see from this map here, which came from one of Paul Hessey's papers, that most of the dates are from the eastern deserts, and we know very little about the temporal evolution of the dune fields in the west. So that is definitely something that I want to look at with some of the data that I'm collecting. Okay, so I hope that hasn't been too far out of left field for this conference. I really do appreciate being given the opportunity to talk. I should say a few thank yous. I'm currently funded by an ABRS taxonomy research grant. I'm very lucky that my boss, Scott Keogh, gives me a lot of freedom to work on what interests me. And it's really been so rewarding to talk about these ideas with various geologists and geomorphologists over the years. I just love how they're very interested to talk to me about this stuff, and it just fuels ideas. So thank you very much for listening.
Thank you very much for the introduction, and thank you very much for this presentation opportunity. Good morning, everyone, or good afternoon for some of the participants. So this presentation is led by myself. My name is Naoko Nagumo from the International Center for Water Hazard and Risk Management. We call ICHAM, located in Tsukuba, Japan. So my presentation title today is the sediment transport processes and landform changes during flood events in Japanese mountainous river basins. So as I wrote in the flyer of this webinar, my presentation topic is recent flood disasters in Japan, particularly focusing on the mountainous river basins. So far, we have done a lot of field surveys and investigations soon after the flood occurred, and now we realized how big changes are brought in the river channels and how rapid local livelihoods or assets are damaged by the flood with large volume of sediments. But on the other hand, for us, the floods and sediment transportation are the natural processes to develop the channels and the fluvial landforms. So I think we have to very carefully observe and understand what is going on during flood events in the target river basins in terms of the both hazards and geomorphic landform development. So this slide shows the several photos taken during flood events in our country. And you can find the various phenomena such as the inundation. So this is also inundation, or the erosion, bank erosion, or the slope failures have been occurring. So they, due to such hazards, based on the Cabinet Office report, approximately 97% of municipalities over Japan suffered one or more flood disasters in 10 years from 2009 to 2018. And more than half, which is the 56.6% of local governments suffered flood disasters more than 10 times. And consequently, the only 2.88%, which is the 48 local governments or municipalities, have been experienced no flood disasters. So this is a situation. And also the as the same as the other regions over the world, the rainfall patterns are changing, and we have the experienced more intensified rainfall than before. This figure shows the number of the short-term rainfall, which is the over 50 millimeters per hour between 1976 and 2020. And this kind of the short-term rainfall is increasing, and the number in 2020 became about 1.4 times compared with the case in the 1976. In addition, the number of serious rainfall events with over 1,000 millimeter rainfall in total are frequently occurring now in our country. And the further, considering the further climate change effects, so this kind of the heavy rainfall and related flood events might happen more frequently and seriously. So the right figures show the course of typhoons and the average number of typhoons born, approached, and landed per month. So the as you may know, the Japan is affected by monsoon, and the rainfall has the seasonality, and the number of typhoons increase from July to September, October. And the 3 typhoons in average have been landing to Japan in annual. So the average, the typhoons also encourage the frontal activities. Then the heavy rainfall are provided in that season every year. So the average, the annual rainfall, as the left figure shows, for example, Tokyo is less than 2,000 millimeter, maybe around 1,800 millimeter in a year. But at the time of the hazardous rainfall in rainy season, so we often obtain the several hundreds millimeter rainfall even in a day. So in addition, we have the quite steep landforms. So as you may know, here is the very famous Mount Fuji in the central part of the country. And also there are high elevation areas of about 2,000 to the over 3,000 meters in the middle part of the islands. As well as we also have the active volcanoes. Because of our country is located along the Ring of Fire and at the junction of the 3 geological plates of the shown in this figure. So the once heavy rainfall is provided to the such the mountainous landforms, the bed slope of the river is going to be very steep. So as you can see in the bottom right figure. So these are the longitudinal change of this bed slopes in rivers in Japan, the others are different countries. So the flood reaches in the downstream of the river basin very quickly, maybe within 1 hour or the several hours after the rainfall in the upstream. And also the erosion processes with this kind of very steep bed slopes. So the flood water and the erosion processes by the flood water are enhanced to produce the much volume of sediments. So this is just an example showing the riverbed after the big flood occurred in mountainous river basin. This is a disaster in it was 2018, and you can see that the river channel. Here is a river channel, but very small river channel, and you can see that the channel was totally closed by large volume of sediments, and the floods expanded the surrounded areas, and that resulted in the serious hazards. So this is the another case. The right photo shows the before the disaster, and the left photo shows the after the disaster. So the compared, if you compare these two photos, you can easily understand the big changes because the large volume of sediments accumulated within the channel. Then the channel change took place in the surrounding areas, and the flood became more serious. So this kind of floods and inundations transporting a large volume of sediments, and sometimes it also transports the driftwoods resulting from it causes the channel closing or the channel changes due to the deposition of large volume of sediments or the driftwoods. So this kind of the flood events are one of the big concerns on the river management or the disaster risk reduction in our country. But another concern is the local people or even the decision makers in the community have not really understood that the heavy rainfall causes not only inundation but also erosion and sediment transportation, which results in landform changes. So we have the flood hazard maps which show risks of inundation, and it is very popular nowadays in local communities. But in addition, we have to explain what kind of the sediment transportation might be occur, and we also have to detect the areas where the landforms can actively be changed if large floods occur on the basis of the fluvial geomorphology. So the motivation of our research is to reveal the characteristics of flood hazards with the abundant sediments and driftwoods, and explain the process, or to propose the indicators that can explain erosion or the sediment transport and deposition processes by the flood waters. And we also need to detect the hazardous areas by the rapid landform changes during the flood events. So I would like to show you one flood case. This river basin with a red line. So this is a river basin boundary. We call Akatani River Basin, which was flooded because of the torrential rainfall, around 6 millimeters in total in 2 days. So this is a river channel, the tributary. You can see that much sediments are distributed along the river channels, and many slope failures in the mountainous areas, and debris flows transported the sediments into the river channel. So this is downstream case, this is middle stream, and you can see that the big change of the channel courses. And this is a case of this is a the plan view of the river basins, that the colored areas are hazard that affected by the hazards. So I quickly go through the slide. And so this is the geological condition. So we have the ground diorite or the schist, so that the very active sediment production occurs. So sorry for the announcement, but I continue. So, so this is the case of sub-basin. Can I stop a little bit?
Okay, yes. So
sorry,
this
is an announcement of my building.
Okay.
Were they announcing a flood was coming?
No, that announcement. Sorry. I continue. So this is the photos of the field surveys. So you can see that this is a sub-basin, the yellow area. So you can see that in the upstream slope failure occurred, and the debris flow transported the sediments, so that the no sediments appeared here. The erosion is very active in these areas, and then deposition became very active. Then the big beautiful cones are created in the valley mouth. So this is the situation of the upstream. And then these sediments are totally transported to the mainstream, and then the sediment, the rivers are transported to these sediments. So this is the situation. So so we concluded that this kind of the schematic figures. So this is the longitudinal profile of the river. So slope failure occurred, debris flow occurred, then flood with sediment and driftwoods occurred in this area. So that to evaluate this kind of sediment transportation, we proposed one indicator. So on the basis of the hydraulic ideas, and I don't explain in detail, but we proposed a very simple way by using the drainage area, which is A, and the bed slope, which is I. And by using the A times I, we could just call it AI. The sediment transport capacity of the river channel can be described by using this indicator. So by using this indicator, we calculated the longitudinal changes of the sediment transport capacity in the river basins. So this is the example. So that the sediment transport capacity increase and decrease. This river also, the sediment transport capacity is not so much, not so high, but suddenly increase and decrease. And actually, based on our field surveys, we observed the area, the heavy, the deposition occurred, or this area heavy, the erosion occurred, we observed. So now we concluded that this kind of the indicator, very the simple indicator, but it is very useful to evaluate this kind of sediment transportation and detect the hazardous area in this kind of mountainous river basins. So maybe I only have several minutes, 1 or 2 minutes, so I move on to the conclusion. So that we reveal the longitudinal increase or decrease of the sediment transport capacity by using the A times I. And then we could evaluate the sediment transport capacity, the changes of sediment transport capacity of river channels, and detect the hazardous areas. So we believe this kind of indicator is very useful, demonstrating the characteristics of floods or risks in mountainous river basins, and which makes certain contribution for the decision making on the local sustainability. So this is end of my talk. And finally, so please allow me to announce one event. So we are organizing the ICFM9, the international conference. So we are the organizer, we are host. So if you are interested in, please visit our website and submit your abstract. The abstract, the deadline is extended 1 month. So thank you very much for your attention. This is end.
Okay, sorry. So my report is on a method we developed recently for measuring the integrated effects of hydrodynamic and eco-geomorphic controls on river channel form adjustment. Can you see now? Hello?
Oh, yes, now it's the second slide, so.
Oh, good. I'll use this one. Okay, we know the river channel adjustment is driven by mostly by flow dynamics, but in quite lots of time, it's also subject to the local ecological and geomorphic restrictions. We all know this, but we have a problem. We are lacking a suitable method to measure the integrated effects. So this is a aim of our study is one, to develop a theoretical-based method to measure the integrated effects, and two, to evaluate the applicability of this method in a case study. In the case study, we chose the Yingchuan Ridge of the Upper Yellow River in China. The theoretical basis for our method is the equilibrium theory developed by myself, Professor Gerald Nanson, and many others since 2000. And our approach is based on the basic flow relations governing river channel flow. There's a Q equals VA, and Manning's flow resistance formula, and also shear stress-based bedload transport equation. So with these equations, but we have 4 variables to solve. One, there with channel width, depth, velocity, and the slope. So there's no closure solution, mathematical for river channel geometry. So how to deal with this? Since 2000, we proposed a variational approach, and we got this. With the 3 equations, we found it's true there's no mathematical collusion solution of river channel geometry. But once we introduce with depth ratio, then we can find once the channel slope or energy slope is given, we can find a sediment transport curve, and from the smaller to the maximum, then declines. And also the one sediment discharge given, then we can find a curve, channel slope curve, with the increase of with depth ratio, channel slope from the large to the smallest, then increase again. So basically, what the result is, there are 2 optimal conditions. One is maximum sediment discharge. Another one is the minimum energy slope. The 2 conditions are inherent in the 3 basic flow relationships. And also we can put the 2 equations, the 2 optimal conditions into one. We named the maximum flow efficiency, E, and represented by the sediment transport discharge divided by the flow energy, QS. Another condition we found actually is a theoretical result is that once the 2 optimal conditions are reached, the QS maximum or S and the minimum slope reached at a specific channel width depth ratio, and there's a linear relationship between the shear stress, relatively increase in shear stress, and the relatively increase in with depth ratio, and which we named the H. And we use the data from the Brawley, and then to calculate the H. And then we found actually from low flow regime to the high flow regime, and the H just equals a constant, equals 0.3. and the plate bed also close to the 3.3. Okay, so what does the age means? We physically reference that the H equals 0.3 reflects the maximum or full hydrologic control on river channel. So in that case, a straight single-thread channel will be developed. In the other cases, H larger than 0.3 or less than 0.3, the conditions reflect the partial hydrodynamic control and the partial eco-geomorphic controls. So in this case, our method shows that the other channel patterns, like braided or unbranching or meandering, will develop. So this is the context of our method. Okay, to test our method, whether right or not, we perform a case study in the Yingjian range of the Upper Yellow River. This is the map of the where the Yellow River draining basin in China, and the top is where the study ridge based, and on the left hand, this is the whole ridge, which is the 190 kilometer long, and over this lines, it exhibits 3 different channel patterns. On the top is the unbranching, and the middle is the meandering, and the lower part is the braided pattern. And this is the pictures shows the unbranching ridge and the satellite images, and also the meander ridge and the braided ridge. The real bed gradients of this ridge are quite flat. You can see these numbers very low. We look at the flow regime change in the study ridge during 1988 to 2015, and we found that annual runoff initially declines and then remained constant for a while and finally get back to the normal condition. But sediment discharge, sediment load actually declined all the time, and from the 1988 to the 2015, it declined almost by 60%. So with such a change of the flow regime, we look at how the channel platform will respond. We use the remote sensing images, and this is the method we interpret the original images. I use some software called the NVA and also other method, and typically for using the NDVI to differentiate the vegetation change. On the unbranched ridge, we found that this is the satellite images we extracted. We found that during the 1988 to 2015, this unbranched ridge consists of 6 islands over the range. Actually, these 6 islands are rather stable and vegetated most of the time. But the channel bed we extracted, we found actually shrinking since 1988. But the in-channel islands remained stable. So this is what we found in the channel platform chain in unbranched ridge. In meander ridge, we found actually from 1988 to 1990, flow in the channel in the red box, we showed in the pictures, shifted from left bank to the right. And the level part of the channel was dismissed, was absent. You can see in 1992 with the formation of a typical meander pattern. From 1992 to 2015, the salinity of the meandering river decreased from 1.3, actually 1.34 to 0.008, and then gradually increased up to 1.48. So big change in the meandering ridge. In the braided ridge, during this time, we found the width of the channel bed increased considerably, from the 1.2 kilometer to the 1.5 kilometer. The number of large in-channel sandbars and also increased considerably. And this part we can't see the vegetated sandbars. They also look at the adjustment in river channel cross-section profiles during this period. And this is the measured cross-sections. The top two are on the unbranched ridge. We can see there are two large unbranches. And one is here, and another one is here. Remainder is stable during this period. In the meander ridge, the channel profiles adjust very significantly from this part to this part. But the channel width, the bankful width, has not changed much, so almost remains stable. But in the braided ridge, the channel cross section changed not much, and but in channel bars have changed their position laterally and significantly. Sometimes here, sometimes close to the right bank. So with this data, we calculated the H number in different in 3 ridges, and with the 30, we calculate from 31 channel cross sections measured data, and we can see here in the unbranched ridge, H numbers varies from 0.25 to 0.6 on average for each unbranched. H number is close to 0.3. But for the meander ridge, H varies around 0.1. And for in the braided ridge, H varies, takes very small value, around 0.0017. So there are big differences in H numbers in different ridges. Why the H numbers changing this way? And we think that we look at the factors of vegetation, riparian vegetation, and bank materials in different ridges. And this is the map, we show this. And in the braided ridge, we found the channel banks are non-vegetated. And banks essentially fine and medium sand, quite sand, so very weak against the flow erosion. And in the meander ridge, the banks are vegetated, and the materials are mainly fine sand at the top and the silt on the top, on the sand at the bottom, so silt on the top. So this is the in the middle part. In the unbranched ridge, there's also the vegetated, and the banks mainly composed of coarse gravel at the bottom and the sand on the top. So on this you can see on the bottom of this part. We also look at the variations of NDVI in this ridge. We found actually NDVI is the least in the braided ridge, but the largest in the unbranched ridge, the low part, the flow from the low part to the up part. And also we look at the geomorphological controls over this ridge, and there are 2 gorges. One is the Shizhishan Gorge. It's located in the exit of the Yingchuan Ridge, and it's here. Another one is the Qingtongsha Gorge, and also there's a dam was constructed there. So the whole study ridge is controlled by the 2 gorges, and so that's a little change in the in the channel slope. This is what we found actually. Now I would like to give a little bit just the conclude and our findings. One is a significant difference we found among the age average values. This demonstrates that the age number is a good discriminator of river channel patterns, and summarize all results with the findings from other parts of the world. And we found actually the age number equals 0.3 for island branching ridges. But for the meander ridges, H is normally take a smaller value, smaller than 0.3. And but for the braided ridges, H takes much smaller values than 0.3. So this is the result. Another one we found actually the small range in the H values for each channel pattern. We think it can be reasonable attributed to the no variations in sediment and the vegetation characters. This is our paper published in Water Resource Research last November, and this is the details of this paper. So with 25 pages. So so maybe if you are interested, please to look at that. Thank you very much.
Kia ora, welcome. Thank you very much for the welcome. Today I'm going to be talking a bit about some collaborative work I've been involved in, kind of, I guess, just sharing some recent developments in river management in Aotearoa, New Zealand, which are fundamentally Indigenous-led, and which I think kind of offer a sense of where things are going here, but hopefully of kind of global significance as well, as we try and work out what it means for a river to be in good condition. So I feel a bit, in some ways I feel like an imposter here, but in some ways I've really enjoyed a reminder of my days. I'm a bit of a lapsed geomorphologist. I actually started my PhD working with Professor Huang in the Qing Huang Tibetan Plateau. I couldn't find a photo with him in it, but I found this one instead. But since sort of about halfway through my PhD, I kind of went in a bit of a different direction and became much more interested in kind of scientific practices of labeling sort of good condition for fresh water and good environmental condition more broadly, how we make decisions about how rivers and the environment more broadly should be. So today, as I said, I'm talking about two pieces of collaborative work I've been involved in, both led by others. One, Dan Hikuroa, which has just come out in a book, and I'll have the reference for you at the end, and another one led by Professor Gary Briley, who a few of you will be well familiar with. And as I said, I feel like a bit of an imposter here for a couple of reasons. One, because I didn't lead either of these pieces of work. I've just been a collaborator on them, but also because I think it's important to recognize that I am a Pākehā scholar, I'm a settler in this land, and I'm going to be talking today about Indigenous-led approaches to understanding rivers from the point of view of a Pākehā scholar who is supportive of these attempts, but cannot claim to be leading them. So I'll start by arguing, I suppose, that stream restoration has two, or maybe more, that's for others to think about, at least two key problems. First, it has been increasingly criticized in recent years for its reliance on what might be called Eurocentric ideals about how rivers should be. If we're going to restore a river, we have to decide what we're going to restore it to and what interventions we're going to make in that waterway. And there has been some increasing criticism over the past 20 years or so of the tendency to restore rivers towards a Eurocentric ideal of how rivers should be. And I'll talk about that through an example in a moment. And secondly, there have been kind of growing criticisms around the tendency towards universal measures of river condition, which tend to have a standardizing effect, which can be kind of positive for trying to understand differences between waterways, but can also potentially be homogenizing. If you're intervening in waterways based on a set of standardized measures as to how rivers should be, you potentially end up with a whole lot of rivers that all look kind of the same. And that isn't necessarily a good thing from either an ecological point of view or from a geomorphic point of view. And in particular, there have been suggestions that attempts at river restoration in the US, for example, have kind of failed to take into account the broader geomorphic context in which river channels sit. And Rebecca Lave's work coming out of Indiana has also suggested, and her other colleagues have also suggested, that the increasing tendency towards market-based stream restoration mechanisms, stream mitigation, banking, and so on may only exacerbate this tendency towards homogenization as through attempts to articulate and kind of defend standards for fresh water, because there's so much money involved. So in terms of the European ideal for fresh water, this is an example of a painting by Thomas Cole in 1836, an American painter, I believe, called The Oxbow, and it represents this ideal version of how a river should be, and it emphasizes kind of a controlled, stable, meandering river surrounded by idyllic countryside, and in the foreground we have this kind of threatening, slightly foreboding wild jungle that is seen as that is kind of portrayed in a negative light. And so for me, this painting kind of represents the ideal that a lot of river management efforts have, intentionally or not, kind of tended to aim towards around the world. And this was fairly well criticized by Matt Condolf in 2006 in a paper called River Restoration and Meanders, I think it's called, where he talked about some examples of these kinds of meandering rivers that have been forced into the landscape based on these European ideals. He talks about one particular example here, which looked like this after the work was complete, and then a couple of years later, geomorphic processes, the river had its say about what it wanted to look like, and it no longer looked anything like it had been left after these river restoration attempts. So that hopefully provides a bit of context from where I'm coming from here. So I'm interested in how in possibilities for thinking differently about how rivers might be and how we might envision river restoration efforts. So to come back to the New Zealand context now, freshwater in Aotearoa, New Zealand has undergone a range of impacts since and through colonization. These impacts have, of course, been for Indigenous Māori themselves, who have suffered the loss and degradation of waterways that not all but many Māori subgroups deem as ancestors. And there's been a real disconnection for Māori from land and from traditional kai, or food, associated with, particularly with waterways. There have also been, of course, and these are stories that are similar to many other places around the world. New Zealand has just experienced them recently and very drastically. Drastic changes in river form and process associated with deforestation, causing rapid sedimentation, as well as active interventions in channels themselves, straightening of waterways, of channels, diversion, culverting, and the drainage of wetlands, and so on. And finally, and these have had also ecological impacts of in themselves, as well as ongoing pollution and extinction and the introduction of invasive species and so on. So like many other places in the world, New Zealand's rivers have been heavily impacted since colonization and as a result of colonization. And because of the importance of waterways to Māori, water has featured heavily in in attempts to find redress as a result of the negative actions undertaken by the Crown through colonization and subsequent to the arrival of Europeans. So in 1975, the Waitangi Tribunal was set up to assess claims regarding historical Crown actions, things like taking land away from Māori. And Māori have really focused a lot of effort on fresh water in this space and through these treaty claim settlement processes that have been going on since 1975. And so Māori put a lot of effort towards regaining tino rangatiratanga, which means authority, roughly, regarding fresh water. And there are two examples here of the kinds of progress that effort of Māori is producing. Or is beginning to produce. One is well, since 2014, a national policy priority called Te Mana o Te Wai, which I'll talk about in a moment. And the second is legislation resulting from one specific treaty settlement around legal personhood for the Whanganui River, which is the longest river in New Zealand. So in 2014, as a result of the action of and the kind of the ongoing campaigning by Māori, the government announced a national policy statement for fresh water, which is kind of the overarching guidance document that shapes resource management decisions in relation to fresh water in New Zealand, which outlined Te Mana o Te Wai, which kind of can be understood as the authority of the river, if you like. That's probably a mistranslation, but or the power of the river. And this emphasized the importance of waterways in New Zealand being managed for integrated and holistic well-being in attempts to foreground Māori aspirations and values regarding fresh water. And in particular, it kind of brought to the stage of central government and river governance in New Zealand the concept of Mauri, which translates roughly to life force, and the idea that river governance should aim to maintain the Mauri of both the rivers that we're interacting with and the people associated with those rivers as well. So this is quite a, I guess the point here is this is quite a, quite a change from previous river management approaches, which would simply outline a set of bottom lines for water quality, for example. Instead, we have this kind of holistic vision for how fresh water might be. And most obviously, I guess the analogy is attempts in the late 90s to articulate visions of river health, which I've written about a little in the past. And I guess what's different here is that this is an Indigenous-led approach, which kind of goes beyond simply a set of biophysical and ecological characteristics for fresh water towards this kind of deeper understanding of connection between people and fresh water. What exactly this means, though, is still very much an open question. The intent of this Te Mana o Te Wai statement has been very strongly supported by local and regional councils, iwi groups, and so on. Iwi meaning kind of tribal groups, Māori groups around the country. But the transformative potential of this has still not yet been fully realized. It is contradictory with some other policy where one piece of policy emphasizes development and economic development and neglects this kind of connection between people and the environment, whereas this very much sees them as fundamentally entangled. So there are still contradictions that are being worked out. What exactly it means for fresh water to have Mauri in the eyes of local governments, whose job it is to kind of implement these rules or this guidance, is still very much being worked through. But I think there are early signs that we're seeing here that it has offered the potential for more place-based approaches to freshwater management, freshwater restoration to begin to take hold as particular community groups and particularly Māori communities begin to articulate what the modi of that local river might mean for them. And so there are some really productive possibilities emerging here. Things like iwi management plans, where tribes are developing their own management plans for fresh water, which sit alongside local council freshwater plans, and the increasing kind of funding and recognition of Mātauranga Māori, which essentially translates to traditional Māori knowledge, or not just traditional, actually, contemporary Māori knowledge as well. So a real focus has come out of this on building Māori capacity to articulate what it means from a Māori point of view, or from diverse Māori points of view, for a river to have modi and to support that. At the same time, slightly more recently, but kind of these different things have all been developing at the same time. We had the Whanganui River, which flows out to the east coast of New Zealand, as I mentioned, is the longest river in New Zealand, which has been named a legal person, as a few other rivers and places around the world have been. And this is the result of, again, of the advocacy of Māori. It results directly from a treaty settlement, in this case, from Taranaki, various Whanganui River groups who have been advocating for the recognition of this river since, not in terms of rights necessarily, but in various forms since 1887. So this is a long campaign to kind of restore, again, if you like, the modi of this river that is beginning, hopefully, to bear fruit. And so this has led to new legislation which recognises the river as an indivisible and living whole, rather than as a set of, ecological thresholds which can be measured and sampled. And what this foregrounds is kind of different possibilities for river restoration in relation to fresh water. So for Taranaki iwi, who are associated with this with the Whanganui River, the river can be seen as an ancestor which carries its own mana, its own sense of prestige, and its own sense of well-being, and very much understand the river in relation to the people, similarly to what I said just before. So this rights framing, again, is still very much being worked through what this really means and what it's going to actually look like in practice. It has been somewhat criticised as a kind of a compromise, which was a compromise instead of maybe giving ownership over fresh water, and Brad Coombs writing about a national park that was also given legal personhood. Has said, revealingly, academic praise is often based on the way personification of nature might realize nature's rights, and is only sometimes based on its capacity to address Māori interests. So there's a kind of a tension here between the rights of nature and the expectations and aspirations of Māori, who which are often assumed to line up as the same, but Brad Coombs would argue do not necessarily, and that these attempts to ascribe legal personhood can be a kind of a way of avoiding that slightly complicated discussion. So I guess to kind of begin to sum up here, I just very quickly have highlighted a couple of examples in which Indigenous-led efforts are leading to, in New Zealand, a bit of a change, I think, in our relationships with rivers and freshwater more broadly, highlighting possibilities for us to think beyond the river channel, to think of rivers and freshwater as a living community of animals, plants, people, ancestors, and water, rather than simply as physical and ecological flows. And to begin to shift away from ideas of human authority over freshwater towards more reciprocal understandings of rights and obligations in relation to freshwater. And finally, I think there's a real possibility here for for the increasing kind of recognition of opportunities to work alongside the agency, alongside the river, to treat the river as an agent rather than simply as a subject of our river management efforts. So to potentially work alongside the river as it erodes its banks and recognize that that can be part of a normal process for a river rather than a problem necessarily that needs to be dealt with. So in terms of implications for geomorphology, I think this work, which is still very early and it's still very much going to see where this ends up, but I think it highlights that for geomorphologists, it's really important to support Indigenous aspirations for fresh water. There's a lot of political potential in here, which particularly in lands where we are guests, it's really important to support those aspirations. But in particular, there are opportunities here, I think, for thinking beyond the kind of Western ideals of how rivers should be as kind of stable, meandering, pastoral scenes in paintings. And I think there are possibilities here for increasing recognition of kind of rivers as living things which adjust and which carry certain relationships with people and with the landscape as well. And that adjustment, as I mentioned earlier, can be part of a normal process of these rivers as agents rather than rivers as subjects of river management. Thank you very much. So this very brief talk was based on a couple of papers that I've been involved in. There are some DOIs that you can grab there. I'm happy to provide them to you if you flick me an email there at brendon.blue@vw.ac.nz. Thanks very much for the time, and thanks for bearing with the token social scientist today. Cheers.